Recorded is rolling. It's Wednesday, February 15th. So, bunch of stuff to do. We're going to start on Unit 3 review. So, here's how you guys did on Dynamics review quiz that you guys just did yesterday. So, awesome job if you were on this list. Right, so, still got a few students that need to take it. So, I haven't handed them back yet, but obviously they're graded. So, you guys' grades are in. And when they do, eventually you get this back to you guys can do a quick correction. So, just like normal. All right, so we're going on to Unit 3. You guys remember Unit 3 was, well, it was a few topics put together. So centripetal force, you guys remember like Plato cancers, PVC pipe, and the string? You guys did the whole lab. It's like a three-part lab there. Okay? And then if you combine that with universal gravitation, there's like an inverse square law between distance and force, right? Like between the Earth and the Moon, for example, there's a force, right? You can put these two ideas together and create orbits. I might have you guys derive orbital speed like later in class today, see if you guys remember how to do that. Okay, so I did on AP Classroom open up Unit 3 multiple choice Part B. So I think I opened that yesterday. So let's have that due Monday morning. So we're on the, and then Monday we'll go over the solutions to that, just like we did for Unit 2 and Unit 1. Okay, and then so I'll probably have I don't think I wrote here. I think we'll do Unit 3 quiz on Tuesday, right? So we've been doing Tuesdays, right? So it's coming Tuesday. Here, let me jot that down here. Right, so quiz Tuesday. Put that right there. Okay. All right, and then right, yesterday I gave you guys a page. Yeah, great. I gave you guys a page that looked like this. I said this was just extra practice for you guys. Here, I'll go ahead and put points in the grade book for you guys for this, and we'll actually do this as an activity today, but we'll just do this as a class. Okay, free body diagrams, which free body diagrams match up with which scenarios. Oh, and which equations. These are all Unit 3 related. Okay, and then I've got some AP Classroom questions that are just extra that put together myself. I'll pull those up at some point. All right, we'll go over those. All right, and then I've got some other keys lined up that we'll do later this week. There are some also open on AP Classroom, but I think I told you guys already. I opened up a bunch of stuff on AP Classroom that is not going to be graded. The only thing that you for sure need to do on AP Classroom is Unit 3 multiple choice Part B that I just opened yesterday. Okay. All right. So you guys get what we're doing next few days. Okay. Right, so let's hit this review bit real fast, and then we'll look at these cards right here. Okay. So one thing at a time here. Okay. So centripetal force. Okay. Yeah, let's look at like the lab version that you guys did. You guys had some mass on a string. The string was looped through this PVC pipe. Okay, there was a weight hanging down here. So here, I'll call it F for force, but you could do like mg, but it'd be like this mass, which would be different from this mass. So I'll just call it F for force. Okay. Okay, and this thing was going around a circle. There was some radial size right here, R. Okay, and if this was if the bottom Plato bucket was in static equilibrium, let's say like it's not moving up or down, is the tension of the string holding it up equal to the force down? Yeah. So this could be a force due to gravity, like the weight of this bottom bucket. And this could be the force due to tension, like the tension force holding it up. Okay? Is the tension force here equal to the tension force holding this in a circle? Yeah. And in fact, you could say that this tension force holding this one in a circle is acting as the what kind of force? Centripetal force, right? Now, if you want to be really strict about it, you can say, well, this one has a little bit of weight too, and so maybe there's a little bit of Pythagorean theorem going on. So we are simplifying. We're saying it's basically horizontal, which is pretty close to true. Right? Okay. All right. So when you guys did this lab, I split you guys into 3 groups. I had some of you guys change this radial size. Some of you guys changed this mass right here. Well, here I'll rewrite M for mass. Right? Some of you guys changed this hanging weight. Right. So 3 different experiments. And you're saying, well, how does that affect the linear speed v as it's going around? Okay? And we put all 3 parts together, and you guys came up with like this tension force, which I'll call the centripetal force because you guys said that's what would basically represent this case, is equal to a fraction. What is that fraction?
MP squared over R.
MP squared over R. That's a good one to know. Good one to have memorized. Okay. Oh, now you guys know you get access to this page on the actual exam. They don't exactly have that formula, but they have one that's adjacent to it. You guys see this one here? It says centripetal acceleration is v squared over r. Well, that is the relationship between a force and an acceleration. You just divide by the mass. Right? So if you put the mass back in here, you just get back to that, right? Right, you guys see that connection? Right? That's okay. Right. Okay. So we got 4 variables, and you can find relationships among the variables. Right. So like here, let's do some stuff here. Okay? What if what if I keep V and R the same, and I triple this mass, this swinging mass? Okay. What would happen to the tension force to keep it in a stable circle? It would also have to triple. That's a direct relationship. Right. What if I keep this mass the same and also the radial size the same? Okay? And I triple the speed? Well, how many times heavier would this hanging canister have to be if you triple the speed?
Multiply by 9.
9 times. It have to be 9 times as heavy. Keep the same size circle, same, right? Everything else the same, right? Because that's a square relationship between this force and this V, right? What about this? What if I keep this mass and this V the same, but I want to make a larger circle? What if I want this radius to be 3 times as large? How would you have to adjust this hanging weight?
By 1/3.
A third is heavy, right? You guys see an inverse relationship between these two right here, right? And AP looks for those kinds of relationships. Right? Can you figure out relationships like that, right? You guys got that? Right, now, there was kind of a modified version of this. I think back to rotational kinematics, right? You get, what if you have a turntable? Right? Where's mine? Okay. Get a visual for you guys going on here. Okay. You guys remember turntable physics? Right? So I got 3 Roosevelts on this turntable. Do they all have the same angular velocity, the same turns per time?
Yeah.
Yeah, they do, right? Do they all have the same linear velocity, like radar gun speed? No. Which one's moving the fastest?
The outer one.
Yeah, the one on the outside, right? Okay. So what forces keeping them in a circle, acting as the centripetal force?
Friction.
Friction force. Friction force, right? So if you did like a free body diagram on any one of these Roosevelts, okay, has a weight acting down, has a normal force acting up, and a friction force pointing which way? Towards the center of the circle, right? Isn't that the way centripetal force always acts? It always pulls things into the center of the circle, right? Okay. Now, if you're along for the ride, if you're like a ladybug standing on one of those, it might feel like you're being thrown out like a centrifugal force, but from our inertial frame of reference, say no, this is actually a centripetal force that's pulling them into a circle. Okay. So turntable physics. Okay. So we got this coin on a turntable, and if we're looking from above, all we can see is this force, and that's the friction force acting as a centripetal force. Okay. So we can say that's equal to centripetal force equals, okay. And there was like a modified version of this that we used that actually was not a fraction anymore. What's the other way? M times omega squared times R. There you go, like that, right? Do you guys remember, like if you know one of these, you can drive the other. As long as you know that linear speed is equal to angular speed times your radial distance from center. Like, do you guys remember all the Roosevelts had the same angular speed? You guys just told me? They all have the same omega. But there are different radial distances from the center. R. That's 3 different distances from the center, right? Right? In fact, if you're 3 times as far out, you should have 3 times the linear speed. But they're all moving the same turn per time, right? So if you take this expression and you substitute it into this V, you do, okay, that's omega squared R squared. One of the R's cancels. Oh, and you get exactly this expression right here. Right? You guys can do turntable, centripetal force too. You guys get that? Okay, so that's a quick recap of centripetal force. Okay. The other part of Unit 3 was universal gravitation. So say you got a couple asteroids, maybe the Earth and the Moon. I'll call this one capital M for its mass. I'll call this one lowercase m for its mass. Okay. Some textbooks do that. Some do M1 and M2. Okay. Let's say the distance between those R. Okay. It's usually considered R because a lot of times you have some kind of revolving situation like an orbit, and this could be like the radius of the orbit, right? Although it doesn't have to be, I guess. Okay. Oh, and aren't we going from center to center? Isn't that true? Right? Center to center. I'm not going surface to surface. Unless I'm thinking about like tides or something, then I might do, okay, well, there's different distances, but center to center. Okay. And what is the, here, which, let's say it's like the Earth and the Moon, right? There's gravitational attraction between the two. Right? So the Moon is pulling the Earth this way, and the Earth is pulling the Moon that way, right? Okay. Now, guys, which of these forces is bigger? The Earth pulling the Moon, and the Moon pulling the Earth? They're the same. That's the third law, right? Right. So it's the third law of Hare. And what is that force equal to in magnitude?
GMM over R.
GMM over R squared. Right. So, like, if you double this mass in isolation, you'd be doubling the gravity force, right? Or if you left that one alone and double this one, you'd be doubling force, right? What if you double both masses? What happens to the force? Quadruples, right? Because times two is quadruple. Okay. All right. What about this? What if you take this R distance between them and you triple the distance? Now what happens to the force? It's 1/9 as much, right? Is that true? Right. Or if you cut it into a third, now you got 9 times the force, something like that, right? You know what else you can do with this too? It's like a variation on this. Is what if you're standing at the surface of a planet? Surface of a planet, and this planet has some fixed radial size I'll call capital R. Sometimes I try to push to the capital R for a fixed radius. Okay, and you want to know, hey, what's the gravity field of this planet? Okay. Guys, what's the gravity field of that planet? GM over R squared, right? Which looks a lot like this, except here, you just about here, if you take the gravity force between this guy and the planet and you divide by his mass, now you get an acceleration, like free fall acceleration, right? Because you guys know this is back to the famous Galileo experiment that I keep bringing up over and over. You have different objects. These have different masses and different weights, but if I drop them from the leaning tower, which one hits the ground first? Same time, because they're going to accelerate the same, right? Ignoring air drag can't happen, right? Okay, is that true? You guys know all that? All right. Here, guys, what is capital G? There you go. Universal gravitational constant. Okay. Now, if you wouldn't expect you to memorize this, do they actually have it listed here? They do. They have it listed right here. 6.67 times 10 to the negative 11. They went with base SI units. Okay. So I know it is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Right? They got meter cubed divided by kilogram second squared. I guess alternative, you could do that. Right? Okay. Right. So you guys know that? All right. Now let's take these two ideas. The idea of centripetal force. Let's go back to the original Plato canister lab, which is this right here, mv squared over r, and universal gravitation. Where's my? Oh, they're right on the other side of the same paper. I did. Right. GMM over r squared. Okay. Let's put those two ideas together and get orbital speed for a satellite. So now I'll have a planet. Okay. And a lot of satellites are in, but like low Earth orbit, that's only a few hundred kilometers up, is pretty tiny compared to the radius of the planet. So a lot of times you can just say, well, what is the radius of the planet? And say it's orbiting at pretty much that level. Right? So I'll just call it some value r, right? Some distance r, which might be pretty close to the radial size of the planet. Okay? The planet has some mass, the satellite has some mass, and we're trying to keep this thing in orbit. So we need to give it an orbital speed, call it v. Right? Notice I'm saying speed. You could say tangential velocity, that would be okay too. But is the velocity constant? No, because it's going around a curve, right? So its direction is changing, right? Or you could say there's a net force on it, which would also be true. Okay? How many forces are acting on the satellite? One, the gravity force, which is pulling it straight towards the center of the planet, which is acting as the what kind of force? Centripetal force. Okay. See if you guys can drive from scratch orbital speed. Go. You guys get notes up in? Got some paper right on? Right. So drive, what is the speed to keep that satellite in orbit? Okay. In terms of variables, notice I haven't given you any numbers. Okay. There's mass of a planet, there's some radial distance from the center that it's orbiting about. The satellite itself has some mass, that matters. There's a universal gravity constant floating around. So give you guys a head start here. Hopefully some of you guys are getting real close to the answer. Yes, start writing the solution here. That's the setup for that, right? Okay. Okay. So you say the centripetal force is provided by the gravitational force. But again, there's only one force on the satellite. The free body diagram is just here. Break out the painting for that. Here's free body diagram. Boom. F sub G. Done. That's the entire. There's only one force. Okay. It's acting as a centripetal force because it's holding it in a circular pattern. Okay. So here's centripetal force. You guys just told me that. You guys remember that from last semester. Here's universal gravity. You guys told me that too. Say, oh yeah, I remember that. I remember that. Ooh, what cancels out on both sides?
The M and the bottom R.
There you go. Yeah. So the mass of the satellite doesn't actually matter. So if there's the International Space Station and it gets loaded with like new supplies, does it have to speed up or slow down, stay in orbit? No, because it's not doesn't matter. Right? And you're right. Also, one of these stars also cancels, right? So not completely, but partially. Okay. And then if I said solve for orbital speed, you guys are solving for that right there, right? So now you're one step away. Square root both sides. Boom. There you go. Okay. And then, yeah, so if you know universal gravity constant, if you know the mass of the planet, you know radial size of the planet, you can calculate how fast you have to go about. If you plug in the numbers for Earth, so orbital speed, because this is orbital speed, right? For Earth, okay. No, depending on your assumptions, it's about 7,900 or so meters per second, right? So to get up to low Earth orbit and go that fast and say pretty close to circle orbit. Okay. Guys good with that? Guys know that? All right. I think that's been an FRQ question in the past to derive that from scratch. If I remember right, I don't know. There's been a bunch of them. That could be an FRQ in a couple of months here. All right. Next thing. All right. You guys got any questions so far? Okay. So, oh yeah.
Yeah, so in my notes from the earlier unit, it also has the escape speed. How would you derive that?
Oh, escape speed. Yeah. I mentioned that too. Okay, escape speed actually use a different framework. Use conservation of energy. I'll do that real fast. I don't think AP's ever asked about that, but I'll do it real fast. So escape speed is something else. You do conservation of energy. So you say potential plus kinetic, and then if from a universal point of view, actually potential energy is always considered to be negative. So if you send something to the edge of space, it goes to 0 joules if you want to just barely get it there. So you got negative G M M over R. Notice I'm not saying R squared because it's not a force, it's an energy term, right? And it's negative. Plus 1/2 mv squared goes to 0. And this is escape speed. Okay. Anyway, if you go to the algebra, you end up getting escape speed is square root of 2 G M over R, right? Which looks a lot like orbital speed, except that there's a 2 slipped under here, right? 2 slipped underneath the square root. Okay? So actually, if you know one of these, you can solve the other real fast. You just multiply or divide by the square root of 2. Right? So if you take this number and multiply by the square root of 2, the escape speed from Earth, just because I've taught this class so many years, I know it should be about 11,000 some meters per second. I bet if you do this times the square root of 2, you get numbers pretty close to that. Okay. Oh, I got to calculate right here. I'm going to test myself. 3,900 times the square root of 2. Yeah. 11172. Yeah, that works. Okay. Right. Okay. Yeah. Again, I don't think I've ever remember AT asking about escape speed though, but it's good enough. Right? All right. Any other questions? Right. So that is again a real fast recap of what Unit 3 is about. Boom, boom, boom. Put all that together. All right. Let's do these cards that I gave you guys yesterday, right? Because you guys were taking the quiz. A lot of you guys finished early. Thought you probably would. I hand you guys this page. So it has all these different scenarios. This is one of these NMC documents I got last summer. It has these free body diagrams. So which ones match to which ones, and then got some formulas that also describe those. Right, so we'll go through these one by one. Up here. All right. So might be a good idea to like draw on this, or I mean, this is just for you guys, right? So you guys can draw on it, you can write on it, you can write your notes. Start with right, so first one, I got a ball rolled in a vertical circle, and we're looking at the ball right at the very top of that vertical circle. Okay, so go ahead and draw the prebie diagram for that, or match it up to. I mean, it's got to be one of these, right? It's like a 9-part multiple choice. Right. And then which formula would go with that? Because there's some formulas down there too. I think I've told you guys, I'm going to put this in the grade book, but I already gave you guys the points for this. So we'll just do this as a class activity. You don't actually have to turn this in, but I mean, better know how to do all these though, right? All right. Did you guys come up with here? Did you guys come up with this one right here? See, there's a weight acting down, there's a tension force acting down. That's what you guys came up with, right? For the very first one. Boom, boom. That's the math right there. Right? Is that? Okay. And then what if you put that into like an equation? Which equation down here would match with that? Did you guys say that here's the answer key. Here's the answer key. So that matches with that, right? It's two forces down, gravity's pulling down, the tension force pulling down. Okay? And they're conspiring to act as a centrifugal force. Isn't the centrifugal force like the net force? Right? Like the examples we've done so far today, so like you just did like one force, centrifugal force, like the tension or the friction force or the table or the gravity force. But in this case, you add them together, and the combined force is the centrifugal force then v squared over r, right? Is that true? Okay. And you can solve stuff from there. AP might ask a proportional question, they might ask maybe a relative question, or they might ask, say, plug in numbers and solve something. Okay. Speaking of which, I know because AP likes to ask different kinds of questions. The most straightforward thing to do is just give you numbers and plug and chug. Right? But AP likes more proportional type stuff, or like, you change this variable, how does that variable change? And sometimes they'll even give you a window of answers. It's like, well, if you change the speed by this factor, where does it land? It's somewhere between here and here, right? But one trick I've told you guys is that if you just make up numbers for a specific example, you can just solve it and get an exact answer, right? So you could always do that. Okay, so, right, how about this one? So same vertical circle, and now the ball's at the bottom, right? And it's still in motion, right? Still going in a circle. Okay? So, okay, so what would that be? All right, you guys figure out which prebie diagram matches with that? Or maybe draw it from scratch would be even better, right? Okay. Did you guys say that there's a tension force acting up and a weight still acting down? Right, like that? Okay. I mean, the weight didn't change, right? From top to bottom, the weight should be exactly the same as it was before, right? But now the tension is acting up, right? And are these equal and opposite to each other, or is there an unbalanced net force?
Unbalanced.
There is an unbalanced net force, as long as it's in motion. If it's hanging at rest, these could be the same. But if it's in motion, that it's on this curved path, there better be a net force. So now you're going to take the difference between those two, right? Guys know that? Take the difference, and that's equal to now it's the triple force. Okay, guys know that? In fact, I do remember this being an AP classroom question, sort of. It was like where they gave you a range of answers. They said, what if you're throwing a ball in a vertical circle and you're comparing these two? And they said, what is the tension force at the bottom compared to the top? Now, the top, it could kind of be anything. It could go all the way to 0 if it just barely makes it around, or it could be a lot if you're whirling around really fast. Right? The weight is just whatever it is. The weight is its weight. But the tension force could be like anything at the top. Right? But at the bottom, the tension force better be bigger than the weight. Right? And I gave you a take-home quiz back, and this is way back a long time ago, a few months ago. And I asked you guys, what's the tension force at the bottom compared to the top? Now, this is one you had to like sit down and like it probably took 5 minutes to solve. Does anybody remember what's the tension force at the bottom compared to the top? Okay. I think it was if you take the difference between this minus this, it turned out to be like 6 times the weight, right? Regardless of what the mass or the weight of the ball was. So anyway, it takes some time to prove that, but this would be the initial setup for that. Okay. Next one. Oh, a penny spinning on a turntable. Right? I just showed you guys that, right? Broke out the turntable, spinning ring. Okay. So what would the free body diagram look like for something like that? All right, you guys figured it out? Okay, did you guys pick the one that looks like this right here? This right here? Okay. Actually, they didn't label one of those. So we got the weight down, we got the normal force up. Now, are those two equal and opposite?
Yeah.
Yeah, they are because it's not accelerating up or down. Not because of Newton's third law, but just because it's not accelerating up or down. Right? The third law of force to this would be the penny pulling up on the entire Earth. The third law of force to this would be the penny pushing down on the turntable. Okay, but regardless of that. You need two objects for Newton's third law. Okay. Okay, so equilibrium in the vertical direction. And what force is this equal to?
Frictional force.
The friction force. Okay. Now there's also an equation that should go along with this. So let's see if we can craft the equation. So the friction force is acting as the centripetal force in this case, right? Wouldn't that be the case? And what is friction force equal to? What times what? Yeah, coefficient of friction times normal force. Now this is exactly true if we're talking about kinetic friction, which is probably not the case here because it's not sliding. So it should be static. So it can go up to that value. So I guess maybe that's why they didn't actually quite label this, but I could do mu sub s. What if it's like on the verge of slipping? Like it went a smidge faster, it would slip. Then I could say this exactly, right? Right. Okay, so let's just input, right? And then here's your mv squared over r, right? Just like that. And then, oh, the normal force, well, it's equal to the weight, right? And I want to make that substitution because they'll let you cancel something out. They'll let you cancel what out? The mass. So it turns out, I think you guys did a lab version of this back last semester. It shouldn't matter how heavy a coin you have. Now, it should matter the material. So if you have a copper coin versus a zinc coin versus a nickel coin, right, there might be a difference just because of the material properties, right? But if you like stack a lab mass on top of that penny, it shouldn't make any difference as to like how fast you can spin the turntable because mass cancels. Okay. So we got mu times g could equal v squared over r. Okay. This might be like on the verge of slipping, something like that, right? And that's what they came up with here. Mu g equals v squared over r. Okay. Okay, guys good with those? Okay, next one. Block held in place by friction inside a spinning cylinder. This was I know this was one of the college physics questions. I forget if I assigned it or not, but there was like an amusement park ride where there was like a guy riding inside. You guys remember sort of? Right? There was like a coefficient of friction between his clothes and the inside surface. Okay. So you guys have sort of seen this one before. Okay. So what's the free body diagram? And what's an equation that could match with that? All right, so hopefully you came up with this one right here. Right? There's a weight acting down, trying to pull you down. Now the normal force, when the normal force actually be holding you in, kind of like an O'Neill cylinder, right? Isn't that what's hanging above your head right here? It's a giant O'Neill cylinder, right? That's sort of like what that is, right? This inside, right? Holding you in a circle. This is acting as a centripetal force. And you guys know friction force is equal to coefficient of friction times the normal force. Well, we could go like up to that if we're talking about static. Right? So if this is exactly proportional, maybe you have a coefficient of friction that would be like greater than 1, so that this would be like 1-1 ratio, right? This or proportional. Okay. How about equation wise? Well, it looks like I want maybe the friction to be equal to the weight, right? I think we're about to go on a whole journey right here. Maybe the friction force could be equal to the weight. Actually, I should have a step before that. I should say the sum of the forces in the y direction goes to 0, and the friction force minus the weight therefore has to go to 0 newtons. Whoops, back a little bit here. There we go. Okay, so here's the framework. Here's the setup, and then you rearrange it and say, okay, well that must be equivalent to that, right? Or like up to. Now friction force. What is that compared to the normal force? Coefficient of friction times the normal force. Right, wouldn't that be? And in this case, which force is acting as the centripetal force? The normal force in this case, right? Okay. So shouldn't I substitute that out right here? Okay. So mu mv squared over r is equal to mg. Right? Ooh, what cancels on both sides? Mass, right? Right there, right? You got to go to. Okay. All right. And then, okay. Well, I bet the answer is going to look some version of this, right? So let's see what they came up with as the answer. They said g divided by mu is equal to v squared. Oh, okay, yeah. All right. So they just took this and divided this mu down over here, and then they got something like that. Although I guess you could write that different ways too. You guys got them out? Right, so in that case, the normal force is acting as the centripetal force. Next one. Oh, car going around a curve. And it does say as seen from above. So this car probably has a weight and a normal force from the road that are balanced out, but we don't really see those from the helicopter point of view, the aerial point of view. Okay. Now let's say it's a flat track. See, if it's a flat track, it's not banked. If it's banked, you have to bring in trigonometry and all that. Let's say it's a flat track. Guys, if it's a flat track, what force is holding the car on the road? It's got to be friction, right? Okay. That's not necessarily true if it's banked, but if it's flat, then it's got to be friction. Okay. All right, did you guys come up with this right here? The friction force is pointing in, right? Of course, there's a couple forces into and out of the page that we don't see, right? And then here, if the friction force is acting as a centripetal force, okay? See, friction force I know is coefficient of friction times the normal force, and centripetal force could be mv squared over r, right? And the normal force could be equivalent to the weight. M's cancel, right? So it doesn't matter how massive the car is. It matters what kind of tires it has, but not how massive it is, right? When I say the tires matter, that's embedded in this mu value, okay? And then wait, is that okay? That's what they got right there. Okay? Mu g is equal to v squared over r. Right? Just like that. Okay. Next one. Ooh, satellite in orbit. We just did that one earlier, didn't we? Satellite in orbit. So you should just have a single, here's the answer. You should have a single force vector, which is just gravitational force, F sub G, right? Or you might call it M times G, that'd be okay too. Okay? And then now this should be a subscript here. See this should say F sub G, gravitational force, is equal to mv squared over r, like that, right? F sub G. Okay. You guys got that? Okay. And then we actually took a few extra steps earlier in class today, because I had you guys substitute in GMM over r squared here, and then solve for the orbital speed. You guys came up with orbital speed is equal to square root of GM over r. Right? You guys good there? Next one. Bicycling over a hill. So this guy is on top of a hill. Okay. Now, if he was at rest, I would say his weight down is equal to the normal force up. But what if he's in motion? He's actually going over the hill. Ooh, you guys imagine that? Imagine you guys are riding over a hill. Your weight doesn't feel like it usually does. I mean, Earth pulls on you the same, but do you feel a little bit heavy or a little bit light going over the top of a hill? You feel a little bit light, right? Now that has something to do actually with like your apparent weight might be something to do with the normal force, right? Like if you go too fast, you can actually like fly off the hill, right? You feel weightless, right? Talk about apparent weight. So what would that free body diagram look like? All right, did you guys come up with this right here? Okay. Got the weight down, the normal force up, and notice there's a net force, right? Could you take the difference between those two, and that would be the net force, which would be acting as the centripetal force, holding them on this dash line curvature, right? Like some associated radius of curvature. That's why they put the circle flush to that hill, right? So there you go. the weight down minus the normal force up, there is a difference there. It's not zero. Okay? That's acting as a centripetal force. Okay. Oh, yes, dude. Okay, so okay, so there has to be a net force that's acting downward because downward is towards the center of the circle. Right. The fact that he's on this curved path and he's in motion, right? So he's not sitting there still. He's actually like has a velocity to the right, right? So the fact that he's on this curved path, there better be a centripetal force that's acting downward, right? In this case, it's the net force. It's the difference between these two, right? See, like if the normal force was equal to the weight, then there would be no net force in the vertical direction. You might be like on a flat track in that case. Okay. But maybe another way to contextualize it is if he goes too fast to like fly off the hill, like what if he's going like 88 miles an hour, flying off the hill, then he would feel weightless. And feeling weightless is the same thing as just being in free fall, right? So then the normal force would shrink all the way to zero if he's like flying off the hill. Right? So maybe that could be like a boundary case. In fact, you know what, too? That actually leads to orbital velocity, right? Because if you just turn this into the Earth, right, you get rid of this guy, right? Then this turns into that. Same as orbital velocity, could be, right? You're like flying around the Earth. Ooh, conical pendulum. Ooh, conical pendulum. Gonna do some work with this one. So what's the free body diagram? There's only a couple left. All right. So we're, hopefully you guys were thinking this right here, right? There's the weight acting down, and there's the tension force that's acting up at some angle, right? That's what you can call it. Now, what's an expression that could relate these variables? All right, now here's where we're going to do some work with this. This one's going to take some thinking. I mean, we've done this before, but okay, dashed line. Okay, we're going here. Okay. Guys, which force is larger in magnitude? The weight acting down or the tension force acting on the angle? Which force is bigger? Yeah, has to be the tension force. Right. Okay. And the reason is here we got two force equations we're going to set up. I'm going to say the sum of the forces in the y direction. Guys, what is the sum of the forces in the y direction? Zero. Yeah, zero. Because this ball is definitely not accelerating up or down. Right? It's staying in a circular plane that's just horizontal. Right? So if you break this tension into components, okay, say the tension is partially pulling up and partially pulling to the right. So now I've got it in components in terms of Earth gravity. Okay? Would this would this angle here that they listed on the in the diagram be exactly equal to that angle? Same angle, right? Okay, if that's 29 degrees, that's 29 degrees. Okay. Wouldn't this bit right here be ft times cosine of that angle? All right, time up here. Pause this.